Okay, it's 2 minutes past, so we'll kick off. So it is, once again, great pleasure that I introduce this week's speaker, who is Professor Dénes Szücs, and who is a professor of cognitive neuroscience and psychology at the University of Cambridge. He's also Deputy Director of the Centre for Neuroscience in Education at the Department of Psychology in Cambridge, and is an official fellow of Darwin College. In addition, he's a senior fellow in the science of learning at UNESCO. Dénes was a recipient of the James S. McDonnell Foundation Scholar Award in 2013 and elected as Fellow of the Association for Psychological Science in the States in 2019. Today, he's going to be talking to us about his work examining cognitive and emotional factors related to maths learning, including mathematical learning difficulties and maths anxiety. So I will hand over, I'm going to turn my, my video and my microphone off and hand over to you, Dénes. If anybody wants to ask questions, just pop them in the chat and we will address them at the end. So off you go.
All right, thank you very much for the invitation. And I note as well that I do have a cold. So if I suddenly have to cough, I try to mute myself. Unfortunately, it just surprised me. So thank you for the invitation again. And what's special about math? I think one special characteristic of mathematics, even at early ages, in young children, is that even simple mathematics requires very complex cognitive processing. So if you try to execute just this very simple operation, you can go two ways. One is wrong, one is correct. Of course, then you have to carry out a very large number of mental operations. You have to operate on lots of operands. You have to know lots of rules. You have to apply lots of knowledge. So even a simple, seemingly simple mathematical operation, if you want to execute it, requires a lot of mental resources. Consequently, we can assume that lots of cognitive skills may be associated with mathematical development and mathematical mathematical processing in general. So you can think about some domain general knowledge, domain general skills as being important. You can see some of them listed here, and some domain specific skills may be considered important as well. Of course, we can think about general specific knowledge about mathematics, and some researchers assumed that a so-called approximate number system or number sense is an important factor, domain-specific factor behind mathematical development. Emotional factors are also strongly influencing mathematical development. One of them, which we studied fairly extensively during the past decade, is mathematics anxiety. So we'll talk about these factors here. In one of our previous studies, we have done a modeling exercise on the data of about 100 children. So we measured a very large number of variables with this population, as you see here on this horizontal axis: visual spatial working memory, short-term memory task, block design from the WISC, phonological decoding task, WISC vocabulary task, Raven's intelligence scale, and so on, spatial orientation, sustained rotation, and sustained attention, mental rotation task. And we also use several measures of the approximate number system. You can see here, tray making task, a measure of task switching, executive functioning as usually is used. And you can notice that the most surprising may be that nearly everything we measured did correlate with mathematical achievement. So all these bold dots stand for significant correlations. You can see bootstrapped confidence intervals there. So it seems harder to find something which is not correlated with math development than to find something which is. We actually did manage to find some measures which were not correlated with math development. Some measures of the ANS or approximate number system were not correlated with it. So this study gave us some ideas about the complexity of mathematical development and the variety of cognitive factors behind mathematical development. Sorry for my voice, I hope I won't lose it. And in a regression model, then we looked at these measures associated with math development, and we tried to make sense of them. So the most important ones, according to our very systematic model building, were some phonological measures and the whisk vocabulary measure, and other spatial measures, visual spatial memory measures, short-term memory and working memory, and a spatial orientation task, and the tray-making task also was one of the most significant predictors of mathematical achievement. So this roughly gives us verbal or language-related measures and space-related measures, memory-related measures, and some kind of measure of executive functioning, which we found to be mostly associated with math development. In our sample of 9-year-old children in the UK. So we suggested a very simple model summarizing our findings. We focused on the memory space as kind of a mental workspace for mathematical action in the mind. So visual and verbal memory would be the center of our model. Executive functions have organizing action, which is fairly important for mathematics, as the very simple example in the beginning illustrated as well. And then simple manipulation is the core feature of human-specific mathematics. We probably rely on both spatial and verbal operations when we manipulate symbols. We could think about symbol grounding, how we link those symbols to meaning, and perhaps that's where the understanding of magnitude relations or the approximate number system may play a role at very early development. But as I said in our data, we did not find Dénes to be associated with math achievement. So this simple model gives us some view on mathematical development and what kind of factors we may want to focus on. So we followed up our previous work, and we carried out a very large replication extension study of our previous findings. So we analyzed data from more than 1,200 children from grades 2, 4, and 6 in Italy. This was done with in collaboration with Irene Mamarella from the University of Padua. We measured math achievement, and as a control, also reading achievement in these children. We also had an IQ score with them. We measured several measures of the approximate number system. We used a dot comparison task for this, and we derived several measures of the Dénes from this task, or the usual measures used in the literature. We also used the symbolic number comparison task. Here we tested symbolic number comparison decision accuracy and reaction time. We also derived some measures of the so-called distance effect, which would be a measure of a representation, perhaps behind symbolic numbers. And then we tested short-term memory and visual and working memory, both in verbal and visual domains. We had, as I said, grade 2, grade 4, and grade 6 data. And here you can see zero order and partial correlations with mathematical achievement scores in this first column for each grade. In the second column, or rather 2 columns, you can see a base factor summary for the correlation measures. Now, the first number here, 1 or 0, stands for whether the alternative or the null hypothesis was supported, and the second number gives a level of evidence we could measure according to a typical base factor scaling used in publications. If you see a little star, that means that the support for the alternative or the null hypothesis swapped over after carrying out partial correlations. So actually it's not that difficult to interpret these tables as it may seem for the first time. So here now we can focus on the correlations we measured between math achievement, between our math achievement measure and the approximate number system measures. The top 3 lines show correlations with the so-called W, an often used measure of the approximate number system. You can see that 0 order correlations were extremely low. The highest levels of correlations were achieved in grade 6, but this is only minus 0.18. In partial correlations, the correlations usually decreased. If we considered other measures, which are basically accuracy, for example, is giving you the same information as W, it's just another view on the same information. So you can see that 0 order correlations were again very low. Here we have the highest one. And then in grade 6, we had 0.18 correlations. Again, reaction time was a very weak correlate of math achievement. So actually in our data, we could say that we replicated a previous paper from Justin Hubbard and colleagues, which used a very large population. They measured W in this large population, and they used self-declared math scores as a measure of mathematical expertise there. So they measured a minus 0.13 correlation between W and self-declared math expertise. As you see, we measured an even higher correlation than that, so we could say that our results are stronger than they were there. However, if we look at the R-squared, then it's obvious that this correlation is really low, so we can't really use this W or approximate number system data for any kind of prediction, any kind of diagnostic purposes, in my opinion. Now, if we go further, we can look at correlations with, between symbolic number comparison and our math achievement measure. You can see that symbolic number comparison decision accuracy was moderately correlated in grade 2 with math achievement scores, but this correlation dropped later. Reaction time showed a little bit of an opposite pattern, but these are still fairly low correlations. Measures of the symbolic distance effect, we could say, were very weakly correlated to math achievement measures. In partial correlation, it is very weak outcomes. It's important to emphasize here that symbolic number comparison is a skill directly relevant to school mathematics. So it is not really a measure of cognitive representation, in my opinion. We are measuring something which is taught in school implicitly or explicitly, how you compare numbers to each other. From this point of view, it wouldn't be very surprising to find a correlation between this measure and math achievement scores in early years. But these correlations are still fairly weak. If you look at short-term memory and working memory related findings, then those correlations are stronger than the previous ones, except for visual spatial short-term memory in grade 4 and grade 6. You can see we have somewhat more robust correlations between math achievement and our short-term memory and working memory measures than in case of the other measures. It's also interesting to think about the correlation between our Kettle IQ measure and math achievement. So that's the IQ score we used in partial correlations. So overall, from this study, we concluded that we couldn't confirm that ANS would be related strongly at all to school level mathematics from between grade 2 and grade 6. And the strongest predictors of math achievement we found were symbolic number comparison accuracy, and reaction time and spatial working memory and other working memory measures you can see here. I'm not sure how I muted myself. It was unintentional. Sorry again for the occasional coughing, near coughing. So it's also important to comment at this point that in the past we have also done a review of number sense training studies in children in 2017. We have reviewed all the available studies at that point, and we have identified several problems with those studies. Study design was often very weak, power was often very weak, statistical implementation was often problematic, inference was very biased very often in those studies, and on the other hand, some training studies were cited very uncritically in support of positive claims about the usefulness of numbers as training. So our findings in this big empirical study I have just shown also confirm in line with our conclusions in this review, earlier review paper, that perhaps we shouldn't assume that ANS is so related to numerical skills and as it was thought before. And recently, a larger study appeared as well in 2021 with a larger sample size with more than 300 children from authors who previously ran numbers and training studies. Their conclusion was that they failed to replicate the benefits of the approximate arithmetic training for symbolic arithmetic fluency, at least in adults. That's kind of confirming our conclusions from this review paper. Now, this brings us to the importance of replication in general, and I think we initiated the first big replication study in mathematical cognition. This was published in 2020, and we aim to replicate a 2003 paper from Nature Neuroscience, which provided some crucial evidence for an automatically activating mental number line. So here the finding was very simple. If you present a number in the middle of the computer screen and later you present a lateralized target, then if that target is on the left, then a small number would accelerate the detection of the left target, whereas a large number would accelerate the detection of a right presented target. What is small and what is large depends on the number range you are presenting. So it's a very simple finding in principle. Again, it was used as a crucial bit of evidence suggesting that numbers are very strongly associated with spatial information. So strongly that this association would be automatically elicited. Now we have done a large replication study with 17 participating labs with more than 1,100 participants. You can see the participating labs and the sample sizes from these labs here. And you can see the original findings from the 2003 paper here. These are interstimulus intervals for number presentations. They use multiple. These are the original findings. You can see the effect sizes here in terms of milliseconds. So these are not meta-analytic estimates, but actually measured in milliseconds for the original study. And here you can see our replications. The original model is an exact copy of the previous study's model. You can see our effect size estimates. These are now meta-analytic estimates integrating data from all of these labs. So we are close to zero. You can actually see the effect sizes here with numbers as well. So we could say we measured zero effect size at all of these eye size. Now we also considered various moderators in our models. You can see these models here. And then you can see the measured effect sizes, meta-analytic estimates in these effect sizes. They are about zero, where you see larger effects. Large means 1 to 2 milliseconds, maybe 3. Then actually those effects were deviating to the wrong side. So they had a different direction relative to the originally measured effect, except in one single case, but that effect size is again about 2 milliseconds. So our conclusion was that we couldn't really confirm the previous findings. We couldn't replicate the previous findings. So this often cited finding may not be as valid as often assumed. This again emphasizes the importance of replication in numerical cognition as well. We could think about several candidate papers perhaps that we could replicate or aim to replicate. This is just as an excursion, as a diversionary thought, is a general problem of psychology and neuroscience research. We have done an analysis on the published literature with John Ioannidis at Stanford. Previously, considering lots of published papers from the neuroscience, psychology, and medical literature, you can see the degrees of freedoms mined from these papers on this vertical axis here, 20 and 30. Here on this vertical scale, and the effect size is reported in these papers. You can see various journals represented by these little markers here. Red ones are neuroscience journals, and then the green ones are psychology journals. As you can see, the median effect size was about 20-30 in all of these journals. In neuroscience, it was even lower. So this degree of freedom, this level of degrees of freedom is associated with very low statistical power and very high false report probability. So our conclusion was from this study that you can't really trust a very large proportion of the published literature. Lots of published findings may in fact be false. So I think replication, again, is a very important exercise, and that's why my own lab ventured on it now several times. And now another, some other studies of ours addressed some questions about developmental dyscalculia or mathematical learning difficulties. The labeling here is variable. Here, an important question is whether developmental dyscalculia or mathematical learning difficulties can be related to some kind of core deficits. Are they based on some kind of core deficits, when the disruption of a single cognitive skill would be causing problems, deficits, perhaps a 1-0 or nothing style disruption? Or another option would be that children with mathematical learning difficulty simply represent individuals who have extreme values along some cognitive dimensions in a multi-dimensional space. I have argued about this previously, so that would be my preferred option. I strongly suggested that multi-dimensional measurement and considering children in this multi-dimensional space would be an important venture. Of course, it's a difficult exercise because we would need to measure lots of variables and use very large sample sizes. Funding is never enough for that, of course. It's also interesting to think about the variable cutoffs used in dyscalculia research, just as a side note. So actually these cutoffs are extremely variable. That also makes it difficult to clearly interpret the data in many cases. So in a recent study, we addressed a score deficit question about mathematical learning difficulties, began in collaboration with Irene Mamorella and the group in Padua. Our approach, obviously, was to collect a large sample. So we had a sample size of around 1,000 children taking part in this particular analysis. These children are drawn from the previous large study sample, which I presented before. And we had a range of variables. These are the ones we had seen before. So we had measured the Weber fraction, and we had reaction time measures for non-symbolic comparison accuracy for the same task. We had the distance effect observed. We had symbolic number comparison, reaction time and accuracy measures, and we had, of course, short-term verbal memory and working memory in the verbal modality, and short-term and working memory in the spatial modalities as well. So our approach was to compute the standardized difference between math learning difficulty and control children along each measure. We can consider this here as a dimension. It may not really be so, but that's how you can think here now. So we computed these standardized differences in real data. Those are represented by these black dots you can see. So you can see the standardized difference scale on the horizontal axis in terms of coins D. The 0 difference would be that you could not find a difference between MLD and control children. Then we excluded math learning difficulty children from our sample, and we used that sample to simulate a large population with the same intercorrelation matrix between measures as in our control children. And then we computed the standardized difference between math learning difficulty children and controls in our simulated data. So those differences are represented by these red circles. You can see those red circles there in the image. And so here what you can do, we can compare the real and the simulated differences. If our simulated math learning difficulty children just reflect the general properties of our control population, just they are at an extreme level in this sample, then there wouldn't be any difference between these real and simulated differences. On the other hand, the discrepancy between these differences would support the core deficit hypothesis, right? Because real math learning difficulty children could not simply be characterized by the structure of the data of the control children. In that case, they would have something special, perhaps a core deficit beyond the general characteristics, the general structure of our controls data. As you can see, there was never a difference between these measures. So basically, we couldn't confirm that there would be some kind of a core deficit in these children. There was no discrepancy between the simulated differences and differences computed from the real data. So it seems that children with mathematical learning difficulties are only at an extreme position in a distribution which can completely be characterized by the data of the control children. So they don't have any kind of special characteristics beyond that. We could also test the diagnostic power of our measures if we consider them as binary classifiers. So if we use any of these measures, can we use them to classify our math learning difficulty children at all? And what is the accuracy of the classification? Sorry again for this. And classification. What we can use here is a so-called area under the ROC curve measure, or the AUC measure. That's very simply the area under this particular ROC curve if you are approaching from the bottom right corner. So if you are at the diagonal, then we do not have any kind of diagnostic power at all. Then our classification performance is completely random, and that's when the area under the curve would be 0.5. So 0.5 ratio of this whole square. If we are above the diagonal, then this area is increasing. If it would be a perfect classifier, then the area covered would be 1. So 0.5 is the threshold here. That would be the random classification threshold. Traditionally, anything under 0.75 is considered low classification accuracy. And indeed, if we looked at any of our measures, unfortunately, all of them were in that category. So all of them qualified as low classification accuracy measures. So none of them could really determine for us which child had math learning difficulty and which child did not have math learning difficulty. So our measures had low diagnostic power, and we also could not find evidence for core deficit. So children with mathematical learning difficulty and control children were very similar to each other in the sense that the differences just reflect the general properties of a multidimensional distribution of measures. And this distribution can be characterized completely by the control children's data, it seems. So there wouldn't be any kind of distinguished measure which would give us support for a core deficit idea. Oh, sorry. Now I come to some emotional factors. Mathematics anxiety. So we have published a lot on this, so I won't talk about many details. I will just point out at one important finding, which links very strongly with the previous ones about math learning difficulties. So mathematics anxiety is usually defined as a debilitating negative emotional reaction to mathematics, general dread of mathematics. It has a minus 0.3 correlation in most of the studies we have run with mathematical performance. That seems to be a very replicable correlation by large studies. This correlation also can be measured at the country level. If you look at OECD data, then the correlation at the country level between mathematics anxiety and mathematics performance is exactly minus 0.3. So math anxiety can range from the feeling of mild tension to experiencing strong fear of mathematics. It's not necessarily restricted to classroom settings, but can generalize to everyday situations. Here, I would point out that one result, which I think is fairly important. Often I found that there was a very strong preconception according to which math anxiety would appear if somebody would be very weak in mathematics. So it would be an indicator of being poor in mathematics. Of course, if you are poor in mathematics, you will be very anxious about that. I found that as a very frequent assumption. We did a last study investigating whether this assumption holds. You can see our data here. This is nearly 1,800 children from the UK. You can see the math scores on a horizontal axis. Math anxiety scores on a horizontal axis. This is from our math anxiety scale. And then you can see the mathematics standardized scores on the vertical axis. We looked at children who could be defined to have developmental dyscalculia or mathematics learning difficulties. We could call them the DD absolute group here in this particular study. So they had weak mathematics, but would preserve reading. So in terms of their math performance, they were under this mean -1 standard deviation line. And their reading score was normal within the mean ±1 standard deviation range. So those children are represented by the black dots here. And if we consider the math anxiety scale, then we can also select the top 10% most math anxious children. They are on the right of this vertical line. And if math anxiety and developmental dyscalculia would be very strongly associated, then we would expect to find most children with developmental dyscalculia on the right of this vertical line, of course. However, this is clearly not the case. 20% of children with our definition of developmental dyscalculia, which is not necessarily a correct definition, of course. So with our definition of developmental dyscalculia, were on the right of this line, so only 20% of them had high math anxiety. That's of course twice as many as you could expect by our selection criteria, as we selected the top 10% most math anxious children. So actually, children with developmental dyscalculia had a higher chance, it looks like, to have high math anxiety than other children. However, 80% of them were not math anxious or couldn't be qualified as math anxious in our study. And of course, one other important observation to note is that about 80% of children who had high mathematics anxiety are also in the higher ranges of math achievement. So they're in the normal range, or some of them are actually relatively high math achievers. So 80% of children with high mathematics anxiety were normal to high achievers in our sample. So our conclusion is that being math anxious does not mean mathematics stupid, and being math anxious is very unlikely to be the consequence of weak number sense or some other math-specific factor, as it has been suggested in the literature by some. Another interesting correlate of math anxiety to notice is that its main impact seems to be that children are disappearing from the very high achiever range as we move to the right of the math anxiety scale. So here in the very high math anxiety ranges, there are very few children who are very high achievers. So it looks like that math anxiety is actually leading to some kind of a loss of children from that range, from that achievement range. So its primary impact is not that very low achievers will develop high math anxiety, but rather it seems that it's kind of blocking higher achievement, achieving higher achievement ranges. And then we have summarized several of our findings also in a practical way in this Education and Practice series booklet, which has been specifically edited for teachers and practitioners. So there you can find more information if you are interested in. And we have also published the recent meta-analysis on math anxiety, considering several factors which may be important in this literature. Actually, thank you. So that's all I wanted to talk about today, about time. And sorry again for this illness. It's a bit more difficult than expected.
No problem. It honestly was not off-putting at all. Thank you so much for that really interesting talk. We're now open it up for questions. You can either put your question in the chat, or you can raise your hand, put your camera on and ask it if you think it's easier to explain it just by, saying it out loud. Entirely up to you. I will keep an eye on the chat and also the hands going up. Right, so one thing that somebody asked early on was a very simple question. Do you mind sharing your slides? If you don't want to, that's fine, because some presenters don't, because some presenters don't because they want to save it for something else. So entirely up to you.
I'm happy to share them as PDF, so I can send them to you if you heard it. Yes.
Thank you. So somebody has asked, how do you think that math anxiety and math confidence relate?
They definitely relate to each other. One of the correlates of math anxiety is self-efficacy measures. So those are usually considered to be very precise measures of something like confidence. We also find in several studies that math anxiety is stronger in women. I haven't talked about that today because I've talked about that a lot of times. And our booklet analyzes those situations a lot. So usually females show higher levels of math anxiety and lower levels of confidence or perceived self-efficacy in mathematics. So especially gender differences may be related to self-confidence issues as a potential generator of math anxiety. So responding to the question, they are definitely related to each other. The important question will be to decide how the math anxiety and confidence development goes together. For example, lots of females, according to international data, OECD data, for example, are in most countries actually better than males in secondary school in mathematics, but they have lower confidence and higher math anxiety. So the interesting question is when confidence starts to drop, for example. Is it an early phenomenon or is it a later developing phenomenon? In some of our studies, about which I haven't talked here, we found that math anxiety is already stronger in girls in grade 2, 3 in primary school than in boys. So it's something very early appearing as a difference, and often girls are becoming less and less confident in their math skills, even if their performance stays at a good level as they progress in the school system. So how these go together, how they generate math anxiety, is a very interesting question.
Thank you for that response. So there's a question in the chat and also somebody with the hand up. I'm going to go, I think the hand was up first, but I'm not sure. But is it Suza? Is that how I pronounce your name?
Yeah, it's Juja. Yeah.
Juja, okay.
No,
My apologies.
thank you.
Go ahead.
Problem. Yeah, great talk, Dénes. It's great to see you. Dénes and I were like in the same year at in a university in Hungary where we both graduated from. It's awesome work, really impressive. And I have a question about the the results that you presented about the ANS not being relevant to math achievement is very strong and super convincing. I'm wondering if do you see any role for the ANS or like thinking about the ANS for younger kids at all, or you think that it's just basically a thing that like we should just put it away from our conceptual vocabulary? Is it or is it useful for anything? That's basically my question.
So hi, Juja. We haven't seen each other since age. It's a great question. If I could, I would run an ANS testing study in very young children, maybe 3-year-olds, 4-year-olds, if it plays a role. My guess is, I don't have any data for that because I could never run a study like that. If it plays a role, it would play a role early in development. That's my guess, because we have tested now ANS several times in primary school populations, and contrary to some other data, of course, we could never ever find any kind of reasonable correlation between ANS measures and math achievement. We have run one study with kindergartners in 2010, I think. Those were Hungarian kindergartners still. And actually in that study, we couldn't find any kind of relation between ANS measures and mathematics measures we could take with kindergartners. There, this population ranged between 4 and 7 years of age. It would be great to do something like that again. There we had about 60 participants, if I remember well. So it wasn't a terribly huge study. If I could, I would run a larger study. With regards to ANS studies, another very important thing is to consider confounds in ANS experiments, visual confounds. Often they are not considered, and actually quite a few papers supporting the ANS idea did not consider potential confounds in experiments. We published a paper on that as well, and it points absolutely clearly, I think, to the importance of factoring some kind of measures of those confounds in. Otherwise, the measurements may just be meaningless, in my opinion. So in young children, that's probably even more important. And I put back, can you see the slides or not anymore? You can see the slides.
Yeah.
Yes, still. Oops. Wait for it. You see this model. I did put the ANS to the right, where that's indicating that I haven't written it off completely. Sorry. I didn't expect this. Perhaps it plays a role in our development.
Thank you. Thank you.
I will just allow you to have your coughing and your water. And there's a question in the chat, and then Andy has a question. So I'll just go to the chat first. So somebody has asked, so what does correlate with developmental dyscalculia? Do take your time if you're needing to.
I'm trying to come back. Sorry, it's not COVID. I had a test. It's just influenza something. But it's very sudden. So I thought I can do this.
It's fine.
Yeah, the question was what correlates
with developmental dyscalculia?
with developmental dyscalculia. But this picture is illustrative. Usually, we always found something like you see in the previous image. Where memory measures and symbolic numerical decisions were kind of discriminating children who had math learning difficulties or developmental dyscalculia. But when we look at the diagnostic power of our measures, it's not the best. Perhaps a solution would be, and actually that's my favorite solution, I guess, to consider many of these measures at the same time for diagnostic purposes, because of course we have to think in a multi-dimensional space. So children are not one-dimensional. They do not only have an ANS, which is enabling mathematics, but they rely on many cognitive factors, lots of subject knowledge, etc. So we probably have to find a way to consider many of these measures at the same time, and that may allow us to reliably diagnose those children. But one single measure won't do it.
Thank you, Dénes. I'm going to circle back to that question after I've let Andy ask his, because I've got something related to it. But Andy, you go next.
Thanks. Great talk. Thank you so much for that. It's so comprehensive. I want to ask you a little bit about symbolic processing, because I think, as you know, my kind of interest is in science learning rather than in maths. But we see a kind of particular thing that happens in that context that makes me wonder whether we shouldn't be kind of concentrating on this more widely. And I appreciate what you were saying about the notion that symbolic processing is somehow integral to learning maths. But you could argue the same thing about science vocabulary as being integral to learning science. But actually in our data, I was actually talking about it in this forum just last week, you see an interesting thing that actually there's an earlier strong predictor of performance in science in terms of spatial temporal cognition, ability to construct dynamic representations. And on our data, that the effect of that is maintained, but completely mediated by the acquisition of scientific vocabulary at a later date. So what that suggests is actually that what symbolic processing might be doing is facilitating a kind of underlying type of cognition that is central to performance in these types of areas. I don't know if you've had any thoughts about that at all, but I thought I would ask the question anyway.
It's a great question. So here, of course, and you are thinking about a symbolic number comparison task, right? So there's only one task. It's a very focused task. You only compare numbers, usually one-digit numbers, and that's what was the measure here. Of course, it is only one segment of symbolic knowledge. So what would be interesting is to test some larger symbolic knowledge base, perhaps, also early in life and related to mathematical achievement measures. That may be a more interesting measure of symbolic understanding. I'm reaching a point where
if you need to stop, just say so. If it's too much, just say.
I wasn't so serious before because I wasn't talking.
Yeah. I feel like I'm torturing you by making you answer these questions.
Yeah, but did it tell you something? And so far, oh.
Yeah, I mean, sorry, it's it's a complicated area. I think I agree totally about the notion of taking some wider measures of symbolic processing and looking. I just, yeah, well, maybe we can have a further conversation about that offline. I think there's some really interesting parallels between maths and science here that I think merit some further exploration. but not when you've got a very bad cold.
So that's completely unexpected. Wasn't coughing. Not sure what's...
It's the absolute worst when you get that tickle and it just won't go away. I know what you mean. Would you rather stop with questions? Because I don't want to make you suffer.
Maybe that's a better option if you want to avoid some odd videos, but we can try.
Well, I have a question that you could answer by email later if you want to. Or Andy, did you have more to say?
No more from me. No.
The question I was going to ask is that whenever somebody talks about working memory, measuring working memory, I immediately think about measurement because that's what I do. And I'm just because so you saw relationships with working memory, but they were weak, as I understand it. You can just nod or shake your head. And I'm just wondering what the indices was that you used, because we did a study where we took 3 different working memory tasks, and we did 2 things. One, we titrated the processing time of the task according to the child's processing speed, and that strengthened the relationships with maths. And then what we also did was we extracted the processing speed whilst there was a memory load, so from within the working memory task. And that, not on all of the measures, but on some of the measures, contributed to variance in mathematical ability above and beyond storage. When there was or was not, a titration. So it's what we were interested in there, obviously, was about what is it about working memory that relates to maths ability. But I'm always interested to see what performance indices people used from the task to explain the relationship.
Sorry, and then so the question is?
The question was just what types of performance indices is it just straightforward storage, like maximum?
Oh, no, actually, I think in terms of this model, more or less here. So it's working memory. It's kind of a fuzzy concept, in my opinion. Maybe some people won't like me for it.
I agree.
But storage, great. Storage and some of these functions, right? That is more or less the definition of when things become working memory. So we go beyond storage. We do rely on these measures, and we think about mathematics, even these single operations. It's actually non-trivial to tease these cognitive functions apart, by storage ending and beginning, and when you start task switching and refocusing and is requiring more than storage. Strategic planning, perhaps.
Yeah, there's so many different things going on within a working memory task. I agree that and depending on what discipline you're in, they're either called executive functions or they're part of the central executive, or it really depends.
Sorry for my inability to argue properly, but just starts and then.
I know, I completely get it. Might I suggest that if people do have more questions, that they are they able to email you about your talk?
Yeah, sure.
And then you can reply.
I won't cough in email.
Yeah.
You see it.
But I mean, we're 5 minutes from the end anyway, so it's not like we're finishing early. So I will just take a moment to say thank you so much for a really, really interesting talk. I see there is a question in the chat, so we will share your email and then they can send them through. I don't think there'll be a flood of them, but just a few. So thank you for taking the time, and I'm sorry that you had to suffer.
Yeah, I'm sorry too. This really is very unexpected. It just strikes me.
No, but you
about now.
it honestly was not distracting. The talk was great, so thank you. Really appreciate it.
Great. Thank you much again for the invitation. Go out to you.
Thank you for accepting. Go and have a warm cup of tea.
Yes, it is. That's crazy. Bye.
Okay. Bye-bye. Thank you. Bye. Okay, thank you everybody for coming. And I'm going to close the meeting.